Good morning, everybody. Let me just make sure I'm all set up here. Okay, we're recording. I think you can all see my screen and hear me and see me. Let's see, we got about a little under half the class, so let's give everybody another minute and then we can begin today's lecture. Okay, I might as well begin. Someone's already asking some questions about the toy compiler submission. The TAs noticed that there were a bunch of basically broken builds or stuff that wasn't running. And someone's also asking about spacing. So I made a little mistake on Piazza saying that all of the spacing was space characters and not tab characters, but I didn't realize that what I had done is I had just copied the assembly output from GCC, which had spacing characters in it without using the \t. You can just copy the tab character itself. But if you have spacing issues, don't worry about that. The TAs are going to grade ignoring spacing. Diff really does character by character comparison. So just check by hand, or yeah, I mean, you could write scripts to like replace all the white space and stuff. But yeah, diff is not as sensitive to white space. So I mean, it's good to do this anyway, just to make sure that the assembly code you're getting is what you expect to get. So somebody says diff W ignores white space. Is that also white space between characters though? Ignore all white space. Oh, okay. We'll see. Yeah, if that works, then do that. And you can try that. Let's see how that works. Let's see if it ignores all white space. Okay, it does. So we just use diff W. Thanks for that. Thanks for that tip. But also importantly, a lot of people, some people's submissions were just not compiling. And this is what's nice about having the repeatability of a source repository. You don't have to wait for us to grade you. You can check. I mean, this is true and really in all programming. You can validate or at least test to some degree the code yourself. So what you can do is you can just run git clone on your project's URL. So whatever it might be. If it's, well, let me start up my toy compiler repository if I made one. You can just clone your own repository. Oh, I never actually put anything in there. Let me see if I put something in the sandbox. You can always just double check your work by cloning your own repository to a new one. So if you get the message like this where you can't, repository not found. All right, I don't have my SSH key set up in Vagrant. So you can always just reclone your own repository and go into it and just run make in there, and you can test it yourself. This is exactly what our automated grading scripts do. They just run git clone, go into the folder, run make, and then run the test. And so this is what's really, this is what's really great about programming and computing, is that you don't require, you can just automate checking. There's no need to wait for someone, some person to give you the imprimatur of correctness. It's correct because it's like physically verifiable on a machine, which means you can do this yourself as well. So yeah, make sure you do that. Some problems might be maybe you forgot to add the right source code to your repository. Git Status really helps with this. So Git Status ideally should have just say working tree is clean. There's nothing to commit. If you have some extra files there that you don't want to submit to Git, like .o files, you can use a git ignore file. So anyway, yeah, but make sure you double check your repository tonight before we grade it, because it's the toy compiler, I arranged it as a homework. So you get half off for late homework. But for the regular programming project, you'll be able to resubmit with a very small penalty. But yeah, just double check that your repository is set up the way you expect. And remember, you don't have to wait for somebody to grade this. With version control and computing, you can just validate this yourself. Let's see, what other reminders did I have here? Yeah, okay, so are there any, so what kind of questions, now that I think most of you have done the toy compiler, at least implemented it, what questions do you have? Let's see, so there were some early questions here. How do you know that we can see your GitHub URL? This was supposed to be submitted, I think. Yeah, I think you were just supposed to submit the GitHub URL as the submission for your assignment. So toy compiler follow along. Yeah, you in web courses, you submit your GitHub URL. Oh, so the issue is that it's private. So it's private to web courses. Web courses, that's why you get a 404 from the web courses preview. So we have access to it as owners of the GitHub organization. Yeah, no, yeah, yeah. I know that can be like confusing to see that it 404s from web courses, but that's because they're going out and trying to access that page. So let's see. So somebody asked which version of the toy compiler that they need. You only need the one from 9.11. You don't need the compiler version, but you can certainly submit the compiler version if you like. Yeah, you don't need to push any of the templates. The TAs will make sure those are used. When I say make sure it compiles, I mean using make to compile it, using the build. make will call GCC-O as we showed when describing make files. So somebody's asking about not having a new line. I would just double check your printfs to see if you're adding a new line, if it's not where one's not where you expect. So somebody has an error with lexer.c that control may reach the end of a non-void function. Well, it depends on the function. If the function is supposed to, that's a compiler check that makes sure that you're always returning something on every code path in a function that's not void. So just double check that every possible code path has a return statement and every possible condition is being covered. That's a sign that, I talked weeks ago about, one kind of careful way to make sure your specification, your implementation matches your specification, is if you're going to write some code that's conditional, make sure you cover every possible case, even if one of those cases is not expected or an error case. Somebody asked if you already pushed the templates. That's fine. Don't worry about that. Yeah, there might have been an issue with my version of the template where there wasn't a new line at the end of it. So apologies for that. White space is hard for me, I guess. Somebody mentioned also if they weren't using Vagrant, that they had that issue. So make sure you use Vagrant. And I'm going to show a little trick today where you can download these files from within Vagrant. You can download stuff from the web using the command line. Actually, you can even browse the web using a completely terminal text-based browser. And I can show that today just for stuff and giggles. I was about to use the real version of that expression, but yeah, the grades were muted there. So one of the TAs had issues with correctness of their grading. So she muted it until, so yeah, you'll have your grades at some point after, hopefully, ideally within a week of the assignment, because the assignment's not due until tonight. So she was trying to just get ahead on some of the grading, but you have until tonight, 11:59 p.m. Eastern. Okay. Let's move on to the lecture for today. And just a reminder to use Piazza for questions. Some people are still emailing me, and I have a huge. I'm almost reaching 1,000 unread messages in my inbox, and probably many other thousands including the read messages. So Piazza, I check that. If I get a notification that something's on Piazza, I'll check that. I've tried to be pretty good about answering questions on there, and the other TAs also have access to answer questions on there. So be sure to do that to get a faster response. Okay, any questions? So what questions? We talked last time about parser generation and compilers. So any kind of lingering questions from last time or burning questions that you have about this discussion from last time? All right, so today I'm going to just briefly cover this notion of compilers again. And then we're going to look at how we can use a parser generator to automatically generate the parser for our main project, the Simple C project today. So we looked last week, 2 weeks ago, we looked at how to handwrite a very, very simple compiler, the toy compiler. And we saw last week how some of the more tedious parts of that compiler can be automatically generated from a specification. So just as a quick review, recall that with compilers, when you want to write a compiler in a source language, we have this bootstrapping problem, where in order to, our compiler is written in a programming language like C, and in order to compile the compiler itself, in order to generate a runnable program out of it, we have to compile the compiler source code, and that yields some program executable. And compilers are unlike other kinds of programs in that they take source code as input and produce target code as output. So this is what's really hard to wrap your head around when learning about this stuff initially, is that there's really three languages you have to be considering when you're programming the compiler. You have the language that you're writing the compiler in itself, you have the language that you're processing as input, and you have the language that you're generating. And in our toy compiler, the kind of crux of what the compiler does was in that code generation, where we're just literally printing out assembly code in in the most kind of basic way to write a compiler. But also recall that for our toy compiler, we had several phases of processing the input and generating the output. So we had 3 phases in our compiler, all written into 3 individual C files, and all being compiled with GCC to give us our toy compiler. And our toy compiler would take in, it would produce a .s file, and it would take in a .toy file. And writing the lexer and parser are particularly tedious things to do. So what I introduced last week is the flex tool, which can generate lexers for us, and the Bison tool, which can generate parsers for us. So recall that the parser generator takes in some specification of what the parser should do, that is the grammar of the input language, and it generates C code. So this part here is taking in some specification of what we want the parser to do, and Bison will actually generate a C program from that. So in some sense, Bison is a kind of compiler. It's a compiler. It helps us generate the code for a compiler, which will generate code for your machine. And so, this is this nice kind of meta and recursive part of computer science that, some people enjoy. But maybe a simpler way to think about what a parser generator does, or at least what Bison does, is that when you write this Bison file, which is a .y file, it's basically just a C program. So at the beginning of it is just, C code. And at the end of it is C code. And in the middle, you have a grammar specification. And all Bison does is it basically rewrites this file, replacing the grammar with C code. So the parser.y file is basically like a mixture. It's basically a C file, but you're mixing C code with some special specifications that Bison will use to generate C code. So in this sense, Bison is kind of like a compiler. Or if you've ever done like PHP programming where you have template languages, you put HTML mixed in with PHP or Python. It's kind of like this, where you really have a source file, a C source file, but you're mixing in some specification templates inside of that C file. Questions on this so far? Is this sort of making sense? So Bison and Flex just make it a little easier to write the lexing and parsing parts of the compiler. Okay, so let's look a little bit at, let's see, where am I here? Okay, so let's look at how we can write the specification of a parser so that Bison can automatically generate the C code for us. But we have to understand a little background behind syntax and grammars in order to do that. So Bison will make it much easier to write our compiler, but it's using some theoretical foundations to automatically do that. And we don't have to understand those theoretical foundations just to use it. We'll learn about these in a couple weeks, but we do have to understand notions of grammar and syntax to be able to write these specifications. So someone asks, Bison uses CFG production rules, right? So CFGs are context-free grammars, and that's exactly right. So Bison, and this is going into the theoretical aspect. So if you've taken big discrete, you probably will have seen context-free grammars and how they correspond to a type of abstract machine, push-down automata. And we're going to look at that in a couple weeks. But we don't even really have to know a lot of the formal stuff in order just to use Bison to generate parsers for us. But we do have to understand grammars and syntax. So what is syntax? Syntax are rules that govern the structure of language, in our case, source code. And another way to look at it is that syntax defined legal ordering of words in the language. So this goes back to this idea that is illustrated by these two sentences that Noam Chomsky used when he was describing his theories about linguistics several decades ago. So in the first sentence here, we have a sentence that is syntactically correct, but is meaningless. And this kind of illustrates this distinction between syntax and semantics. And the reason that one way we can describe why this first sentence, colorless green ideas sleep furiously, why this seems kind of sensible to our ears, even though it doesn't really have any meaning that we can nail down necessarily, is that it follows syntax. It follows the syntactic rules. And these syntactic rules of English provide restrictions on the legal orderings of words or the sensible orderings of words. So just like in the compiler where we have certain phases that process the input language, each one of those phases in the front end of the compiler is in a sense restricting the valid source code, restricting what source code is valid to be translated by the compiler. So in the same sense, this sentence 2 has no syntactic, it's not valid, it doesn't make sense syntactically in English. By the same sense, our parser will ensure that only programs that follow the syntax of Simple C will be further processed by our compiler. And so if it sees an input that is not syntactically valid, we'll just have an error. And you'll see this in GCC. If you forget a semicolon, for instance, and you get an error and the program won't compile, that's because the parser is saying that without a semicolon, this program is not syntactically valid. You must have a semicolon there in order to have a syntactically valid program. Now, human language is a lot, it feels different because it seems more flexible. But if we take this approach of syntactic rules, it's just that English and human languages just have very, very large grammars with lots and lots of options about what a valid sentence or a valid noun phrase can be. But in spite of that, you can kind of notice in human languages that there are these kind of implicit rules about ordering of words. So for instance, saying a big red car versus a red big car, the latter one in English sounds kind of strange. You would rarely say that sentence in English, but there are these kind of orderings on the ordering of types of adjectives. And if you put verbs at the end of a sentence, you're going to sound like Yoda from Star Wars if you do that. Okay, so we can define the rules of a language using a grammar. And I need to introduce a little terminology to be able to talk about grammars, these grammar specifications. And a grammar is really just defining rules, defining these rules. Well, actually, somebody asked an interesting question. So it would be, so proposing that it would be much easier if languages weren't so flexible. So it depends on what you mean by it, what would be easier. So languages being flexible is much easier for the speaker, right? There's many, many ways to express the same thing. And even if somebody uses a different kind of expression, or somebody, say, a non-native English speaker, and they use what is, what others might think is incorrect grammar, you can still understand it. Or there might be lots of, options for expression. So it depends on what you mean by it. Yeah. So it depends on what you mean by it. So it's certainly easier to process the language. So if you want to write a compiler to automate the translation of a language, as you'll see with Simple C compared to the toy compiler, having to support flexible syntax is a pain from the parsing point of view, and actually a pain from the whole compilation point of view. We'll see that when we look at the Simple C language, how restricted it is compared to C. So C, in some ways, if to some programming language theorists, C is too permissive. You can initialize and declare variables in the same structure. The original C language didn't have that. You would just declare them and initialize them separately. So it depends on what you mean by it would be easier. So processing the language, yeah, if you have a very restricted language, it's much easier to fit the language in a box. It's much easier for the implementation of that language. But it's harder on, as you see as programmers, it's harder on programmers. Now there is an issue of ambiguity in language that if you're trying to have some precise description, it's useful to have, even if the language is really flexible, it's useful to know a one-to-one correspondence between the syntax and the meaning of that language. But that's something in human language that is difficult for precision because you have ambiguity, you have lots of different interpretations for the same syntax, and even the same syntax. But yeah, having a broad syntax is actually, in some sense, more useful for the speaker of that language or the user of that language, depending. I mean, this is, there's no hard and fast rules for this, but that's an interesting question about this. So for ease of implementation, Simple C is going to be a pretty restricted language. It's going to be a very stripped down version of C. Okay, so let's get back to grammars. Grammars define the rules of syntax. And it does this by using rules called productions. And productions just map a name of a grammar construct to the names of the constructs that make up that construct. So I'll show an example of this in a second, but for some terminology, there are two kinds of symbols in these grammars. There are terminals and non-terminals. Terminals are like the tokens, the input of the input language. That's what our lexer produces. These are like the words in the language. And non-terminals, these are the symbols representing the grammar constructs themselves. So this gets a little kind of meta, where we're kind of creating a language to describe the language. So let's look at terminals real quick. So terminals are both in human language and in machine language, terminals are the symbols that are actually present in the utterance or present in the source code. So if you look at a source file and you lex it, you just get a stream of terminals. You just get all the actual characters that are in the input source code. But non-terminals, in contrast, are not actually expressed in the utterance of the language. So when you speak a human language, you have phonemes that make up words, and those words are communicated using sound waves to the listener's ears. And non-terminals, and this is what was kind of speculated in the philosophy of mind by Noam Chomsky and other cognitive scientists, is that even though the non-terminals are not expressed when you speak or when you write source code, there are physical processes that are actually representing the non-terminals of the language. And this is why in a compiler, this is kind of useful for a computing machine, because in a compiler, we will make symbols in the machine to represent those grammar constructs, even if the source language did not include those symbols in the first place. So this is kind of a tricky thing to kind of wrap your head around. But once we actually start writing this parser and looking at grammars, hopefully this will be a little clearer. So somebody asked, aren't there technically 3 symbols, terminal, non-terminal, and start? So yeah, in the formal presentation of a context-free grammar, there's also a starting symbol, but the starting symbol is one of the non-terminals of the language. So it's just a specially designated non-terminal that you say this is where the grammar starts. So as I kind of hinted at, non-terminals are symbols that are not actually present in the utterance or in the source code, but they're symbols that represent the grammar constructs. So it goes back to this theory that the grammar is not just some abstract math notion, but it's actually physically realized with other symbols that are not expressed, but are used to keep track of this structure in the language. And so somebody asked, is 0 through 9 a terminal? So yeah, in our source code, the ASCII codes for digits make up parts of terminals. So as we'll see in the toy compiler, a single digit was one token in our language, and that ended up being one terminal in our grammar. As we'll see in Simple C, if we want to support multi-digit numbers, we need to allow that in our lexer. We need to define our terminals to have multiple possible digits. And I'll show how that works briefly in the lecture specification. But yeah, basically ASCII digits comprise the terminals of our source code. And in fact, because the source code is entirely written using ASCII code, the terminals are only made up of ASCII characters, more or less. So to see the distinction between the terminals and the non-terminals of a language in this colorless green ideas sleep furiously example, here we have the syntax tree for this sentence. So the syntax tree is this hierarchical representation of the pieces, the grammar constructs that describe the syntax of this utterance, of this sentence. And in red here, we have the terminals. These are the actual words that are expressed in the utterance. And in blue, we have the non-terminals. These are the symbols that are theorized to actually be represented in your mind and that are physically represented in our compiler, in our syntax tree. We will physically make data structures that represent these non-terminals. And what the parser does is it takes in just terminals and it basically infers what the grammar tree is, and it builds physical representations of those grammar constructs using a tree structure that we've all learned about in CS1. So this is an example of red terminals that are uttered in our language or written in ASCII code in our source code, and the non-terminals, which are not actually uttered or written in source code, but are inferred by the language processor, whether that's our brain, which is the hypothesis, or our compiler. So physically in our compiler, we will infer this structure and create a representation for it. Questions on this so far? Questions on grammar rules? Another way to look at this is if in, say, elementary school, you had to do sentence diagramming. You probably saw something like this in school if your teacher went over this. And it's really the same idea. It's just showing each of the nested parts of speech that make up our language. And even well before modern computational linguistics, thousands of years ago, there were grammars written for languages. You know, there were scholars who observed this. I think one of the earliest known grammars was for Sanskrit, maybe like several thousand years ago, where somebody tried to write a complete specification, grammar specification of Sanskrit. Sanskrit grammar to just try to describe the language itself. So this notion of having to use language to describe the language itself is an old one in human thought and scholarship. And then to specify these rules in this kind of formal grammar, we have production rules. And production rules just map the name of a construct, the symbol representing the construct, to the parts of that construct. So let's look informally at one of these grammar constructs in Simple C. In Simple C, a program is the top level construct in the Simple C grammar. And a program, it consists of three things. It consists of a list of declarations, a list of function definitions, and a main function. Very much like how you write C programs, although Simple C is much more restricted. But this is just a simple informal description of what a Simple C program, the program construct in the Simple C grammar is. A program maps to a list of declarations, a list of functions, definitions, and a main function. And also notice, just like in sentence diagramming in human language, this syntax has this nested structure. So we can continue to define make more specific definitions of each part of these grammar constructs. And so I can augment this informal description of a Simple C program by expanding out what a declaration is. So this is the same as what I showed on the previous slide, except now this is defining what a declaration is, kind of recursively defining a declaration. And so a declaration is a type specifier followed by a symbol name followed by a semicolon. And notice here that a semicolon is one of the terminals in our language, and a name, an identifier, is also a terminal in our language. These are the actual raw ASCII characters that we see in the input program. So when we look at a full grammar specification, you'll see a bunch of these kind of nested constructs described as production rules. And at the very end of this specification, eventually everything will reduce to terminals in the language. This is actually why they're called terminals, because they terminate the expansion of these production rules. For our parser, we're trying to infer the grammar constructs, but the Chomskyan theory about these grammars were not just that, yeah, languages have grammars, but the theory was that we have machinery in our brains, our physical machinery, that is used to generate language. And so that's why these are sometimes called generative grammars. So rather than in the compiler where we try to infer the grammar construct, the theory that Chomsky introduced was that we have these grammars physically represented in our head. And when we go to speak, we are actually expanding each rule of these grammars in order to produce a sentence in a language. So they were, yeah, that's why he considered them generative grammars. And so terminals are terminals because that's where the expansion of these grammar construct ends. It ends on the actual utterances that we make. So the theory is that behind the scenes in our minds, unseen to the listener, unheard by the listener, we're actually going through these grammar rules to generate language. And then once we reach these terminals, then we have processes that will create create sound waves using our mouths and put phonemes together to create the terminals of the language. And whether or not that's true or not physically, I think it's, there's still controversy in the linguistics field. We can use this notion in a computing machine to actually infer a grammar tree from input languages. Okay, and we'll look at that in the second half of today's lecture when we actually write these grammar rules and generate a tree from them. And we saw this last time a little bit when we looked at the toy compiler. Okay, so we had our informal description of some of the constructs of Simple C's language. So let's look at in the Bison syntax, in Bison format, in Bison input files. This is how we would specify those exact constructs. So it's a little sparse. So we just have to kind of know the meaning of this. This Bison, has its own syntax, it's its own language. This is where I was getting at the kind of meta language, the complexity of dealing with meta languages to talk about languages. But let's just look at it intuitively. This semicolon is basically defining the production rule. And on the left-hand side of the semicolon, This says that a program construct reduces to or is comprised of these three constructs. So this is the same thing that we said informally, where a program grammar construct is composed of three pieces: a list of declarations, a function list, and a main method. And this semicolon, confusingly, is part of the specification of the production rule. This is not part of the input language. So this is where we really need to make clear distinctions between the thing we're representing and how we're representing that. Separating the meta language that's describing the language from the description of the language itself. This is something that's always really tricky to wrap our heads around. But just remember that for a Bison specification, if you want to make a grammar rule, you put the name on the left side, you put a colon to say what this grammar construct reduces to. You give any number of symbols that comprise it, and then end that production rule with a semicolon. This becomes ultra confusing. This becomes ultra confusing if we're processing a language like C or Simple C, because we also use semicolons in the language itself. And we'll see that we use a name, or actually we use a quoted semicolon to describe this. And we'll see this when we look at the Simple C grammar. But just, yeah, you have to kind of sit down and work through it, look at the careful definitions of the Bison specification, and separate that from the language we're trying to define. So this semicolon here is part of the Bison specification, not part of the language that we're processing. And so just to make this, to give you a little preview of the complexity of this, Bison is a compiler, so we're writing the specification of the language we're trying to compile. But remember, Bison itself needs some language to describe the language specification. So we need a meta language to describe the language. But anyway, we can, so the Bison tool itself, now you have to create a compiler for the Bison tool, which is, but yeah, we won't worry about that in this class. And then a declaration, just, very much very much just like what we wrote in our informal specification. A declaration symbol is comprised of these three things: a type, that should be type, an identifier, and a semicolon. And so notice here, I'm making a really clear distinction between the semicolon symbol in the language that we're processing, the Simple C language, versus this literal semicolon character that is part of the grammar specification. This just to beat a dead horse, this semicolon character is part of the Bison production rule, not part of the language that we're processing. So somebody asked, declarations are in references to variables. Correct. So yeah, declaration is the technical term for that part of the, I think it's better to show this. So this construct here, this sequence of characters that you put in an NEC program, this grammar construct is called a declaration. It's like referring to a sentence in English language or human language. You never actually say the word sentence, but we understand the symbol sentence to refer to any utterance that has subject, verb, object, and ends with a period, for instance. And the same thing in C, this sequence of characters that fits this pattern of sequences of characters is called a declaration. So somebody asks about type defing something. Okay, so this is getting into part of the semantics of the language rather than the syntax. So we'll get to this in a couple of weeks. We're not going to implement type defs, but this has to do with, so this is not something that can actually be expressed in context-free grammar. So typing rules can't be expressed in context-free grammars because it requires context information. We'll talk about this in a couple of weeks. But yeah, so grammar, and yeah, so there's this Chomsky hierarchy of languages, types of languages, and we'll get into this once we get into the theory. Type defs and typing they're different. We need a more powerful computational model in order to check the typing rules of the language. Right now, we're looking just at the grammar rules of the language. Okay, so this is basically all you need for a formal grammar definition. And formal doesn't mean, formal has many, many meanings. For a very long time, I thought, oh, formal computer science or formal programming languages means, the kind of conventional definition of formal, like where you put a suit on and now you're formal. Formal just means it follows some pattern. It follows a form. That's formal is like this literal meaning of form. And so a formal grammar just uses some well-defined specification of the grammar in order to describe the grammar, versus the informal definition where we're just using a description in human language to describe it. Formal is really great for computing because a formal specification has some machine readable format that we can use to do automation, like generating a parser automatically from this. So that's all I mean by formal in this sense. Okay, so syntax trees. Okay, so the grammar is in some sense, so the grammar in some sense is defining all possible input programs. And another way to look at that is it's defining all possible syntax trees. It's like a schema for all the possible syntax trees that source programs can be. So in this colorless green ideas sleep furiously example, this tree structure is the syntax tree. The syntax tree is the tree representation of one utterance in the language or one source program. So if we have one C program, that one C program has a single source tree that describes the syntax of that one source program. Whereas the grammar is like a kind of meta description of all the possible syntax trees, or a schema that describes all possible syntax trees that any input program can take. So this is also kind of a point of confusion that many students have, that I also have, this distinction between the syntax itself, which is all the possible rules of the language, versus one particular syntax tree. And in the formal world, this is called the derivation of an input of an utterance in the language. But just think the syntax tree is like, if you've got a single source program, the syntax tree is the tree representation of that one program's syntax, versus the grammar, which defines the syntax rules that describe all the valid syntax trees that any possible input program can take. Is this making sense? Any kind of questions on this? And we'll see this we'll see this a lot when we look at compilers. We have to distinguish between between what a single program does versus what all possible programs do. Well, so so I'm being a little bit imprecise with my language here. So syntax, when we just say the syntax of a language, it's all possible rules all possible grammar rules that language defines. A syntax tree in the computing world is the tree representation of a single program, of a single input program to that compiler. So this is just the distinction between one program's syntax tree versus the grammar itself, which defines the syntax for all possible programs. Does that kind of clear it up? So somebody was asking about this syntax versus grammar. Yeah, so I'm being a little, until we get to the formal stuff, I'm being a little bit imprecise with this language. I'm trying to just give the intuition of it. The grammar is the rules for all possible input programs. And so when we write our compiler, we have to write a parser that handles every possible program. But what our compiler will do is it will generate a syntax tree for any one given program as input. And so it's really tricky to wrap our heads around, because when we think about a program, we intuitively think, well, what is the behavior of this one program? But when we write a compiler, we have to reason about all possible input programs and all possible program behaviors. of all input programs. And it can be, and this is, it's the same problem of the meta language versus the language. When we write the compiler, it's not so, some of the concepts are not so hard, like technically, but philosophically, it's really hard to wrap our head around the fact that we are not interpreting a single program. Rather, we are writing a program that can do the interpretation or compilation of any possible program. So our grammar rules have to account for every possible program's syntax. And it's our compiler that is going to be generating the syntax tree for a single program. But yeah, let me not belabor this too much. We'll see this when we actually start implementing the compiler. I think you'll quickly realize it as you start actually implementing this, and yeah, it'll sort of all come. It'll be like hitting a brick wall. Once you start having issues writing the compiler, you'll start realizing that you have to write a program that accounts for all possible input programs. Okay, so let's look at a little more, try to get intuitively look at how some of these grammars can be described. So the first thing to look at is that the same construct, like a statement, for instance, may have different kinds of utterances. So in the same way, a sentence in human language, there are many kinds of sentences. There's subject, verb, object, there's subject, verb, there are sentences that are just a single noun, there are exclamations. And so to capture this idea that, to basically capture every possible kind of sentence or every possible kind of construct you can have in the language, the way context-free grammars work is you can just define multiple rules for the same grammar construct. So for instance, here is the production rule or some of the production rules for a type, the type syntax. And so so let's look at this declaration again. So remember, a declaration, this is a typo, this should just be type. A declaration is a type followed by an identifier followed by a semicolon. And the type construct, you can have many types in your language. You can have pointer types, ints, characters, booleans. And so in Simple C, for each one of these different kinds of type constructs that we can have, different variations of the type construct, in Bison, what we do, or in a context-free grammar, what we do is we just define multiple rules for that same construct. So here we have a type that expands to either an integer, an int keyword, an int terminal, or we have a type that expands to a char keyword. So remember, this is a declaration of the syntax of the language, of the grammar of the language, not the actual, not an actual input program. And Bison has some syntactic sugar for defining multiple rules for a single construct using this pipe symbol. So we'll see this kind of formatting a lot when I show you the Simple C grammar. This is a kind of stylistic way to write the syntax rules in Bison. So instead we put the non-terminal that's being defined on one line, and then a semicolon to say, well, this can either be an int keyword or, so this pipe is like an or, it's not a logical or, but in the same vein, it's like an or. Yeah, so it's not a logical or, so it's truly a different symbol. So that it's not like an or, but in some sense, yeah, it has some relationship computationally. But just think of it as this is an alternate rule. An alternate is another term for this, or in regular expressions. If you've ever seen, pipe in regular expressions, it's much more related to that. But yeah, so these are the two possible rules that you can have for a type. And we'll see, once we get into parsing theory, we'll see how this is used to automatically generate a parser. But yeah, so that's the kind of Bison specification for multiple rules for the same grammar symbol. Okay, another thing that we're going to see a lot in grammar rules is, so we saw alternation or this pipe. So somebody asked, are we going to use doubles? No, we're not going to have doubles. I'll go over the full Simple C language in the second half of the lecture. Okay, another common thing that we see in grammars is lists. So for instance, in human language, you may have a list of adjectives. So you may say the colorless, green, blue idea. And so you just have a list of adjectives. They all kind of seem like they're at the same level. You know, it's not like a special new construct that says I'm using 2 adjectives now, or I'm using 3 adjectives. It looks just like a list of grammar constructs that are kind of at the same level, a list of adjective constructs. But the way this is done in a grammar is very much like the way you learned about how linked lists works. So remember a linked list versus an array. An array is just defining some contiguous chunk of memory. But in a linked list, you can have an arbitrarily large list of things by having this recursive data type. So where did I? Yeah, so if you, hopefully you all remember this from, I think, CS1, right? CS1 is where you learn about this. In CS1, you define a structure that have 2 fields. One field is the actual contents of the list element. And the next field is a pointer to the next element in that list. And this worked at having arbitrarily long lists of things because there's no inbuilt notion of size of this list. Rather, you recursively reference the same data type in the list data type. And so that's how the data type can be specified, because we're allowed to recursively refer to the same data type itself. This is where the notion of recursion and grammars and language really comes together. Because in order to define lists of things in a grammar, we also use this notion of self-reference. So informally, in the Simple C grammar, if we want to describe a list of declarations, an arbitrarily long list of declarations, we want to do this in a finite grammar. So we want to have a grammar that is, just a single file. We can specify it in a finite number of grammar constructs, but we want to allow an arbitrarily long input language. We use this same notion of self-reference. In Simple C, a declaration list contains a single declaration followed by some other list of declarations. The exact same notion that we have in a linked list. And so to see this using the formal grammar definition, so here's our original program that we had before and our original declaration. So remember that a program contains a declaration list, and we described what a declaration is in grammar rules. But this is the definition of a declaration list. And I forgot the semicolon here, but let's not worry about that. So a declaration list has one rule where it contains some declaration followed by some other declaration list. And so that's the same way that exactly the same way that we use a linked list. So a declaration list says that you can have a declaration under it followed by some other declaration list, some presumably smaller declaration list. So this is not like a variable where these 2 declaration lists refer to the same thing. This is referring to the grammar construct declaration list. And that grammar construct, remember, may have some different syntax tree for a particular input program. And just like a linked list where we end the list with a null, we have a separate grammar construct that just matches an empty string. So this is the way we kind of terminate this list. Yeah, so somebody asked this exact thing that I'm describing, that I was just about to describe. So can the declaration list of that pipe declaration list be empty? Otherwise, how would we know what the last node is? So this is a little bit of a tricky thing that we'll have to get to when we get to formal languages. But we could have also defined this construct to be defined it like this. Oh, don't do that. we could have just defined our grammar construct like this, where we say oh, no, never mind. We couldn't have done that. Well, let's say we defined it by either matching just a single semicolon by itself, or some declaration followed by another list. So this semicolon would be indicating the end of the declaration list. But this is a little weird for the programmer, because that means if we have a list of declarations, we would always have to have some semicolon indicating the end of the list. Or maybe we have the programmer explicitly say, put a period to mean you're ending that list. So in the same sense, so just like in a linked list, this period is like the end list sentinel. So instead of having null, so yeah, the kind of trick in C is that you use null as a sentinel to say what the end of the list is. But you could just as easily say, well, there's a special linked list node, let's call it a sentinel, that you always put at the end of the list. And in a grammar specification, we would do this by having a special symbol, a special terminal that means here is the end of the list. And in our grammar construct, we would match that in an alternate rule for the declaration list. Yeah, another way to do this is we could use a declaration, say that there must always be at least one declaration in this list. So a declaration list can either be a single declaration by itself, or it can be a declaration followed by some other declaration list. The consequence here is that you always have to have at least one declaration in this list. This will become a little bit more apparent when we get into the formal theory of regular expressions and formal grammars, why, kind of the nitty-gritty of why this works. But I think for our purposes, this notion of a sentinel is a little more natural, because we want to allow the developer to not specify any declarations at all if they want. So to make this a little less onerous on the user of the language, we can just have a grammar rule where the right-hand side of the grammar rule expands to nothing, just has no input required in order to match that rule. This is a little tricky to wrap our heads around, this notion of an empty rule or an empty string. So another way to look at it is that this is matching the empty string in the input. And between any two characters in the input or any two terminals, there's an infinite amount of empty strings. And for theoretical reasons that we'll see when we look at the formal definitions of these grammars, we're allowed to have a production rule that matches an empty string. And the way this works out is tricky, the way this works out. But just sort of understand this as an idiom in Bison, where we can define a list as either the list containing an empty string or the list containing some element followed by another list. So somebody asked, can the declaration list, let's see, otherwise, when there are two definitions such as that declaration and declaration list, does Flex just choose the first valid option list? So it's Bison that's doing this. But when we get to the way parsers work, we'll see how and why this works. But basically, the parser is free to match an empty string at any point in the input. Because, I mean, just think about it. Between any two terminals is an infinite amount of empty space. And so it's kind of it's almost like a theoretical conceit that the parser or the grammar can use to match an empty grammar rule. I think it might be helpful to look at what the syntax tree of this looks like in order to understand why we match an empty string for this. Okay, let's look at let me type some of this. I think it's easier to read. My handwriting is quite bad, so let me type some of this. let's do it like this. So let's say we've got a list of declarations in our language. And remember, new line characters are just white space that are basically ignored by both C and simple C. So we could just as easily write our C code like this, where all of the declarations are just on a single line. There's nothing special about the white space when processing C. Some languages like Python do use white space as part of the syntax, but C and simple C do not. Okay, so here's our input program. And let me just show you what the syntax tree for this declaration list looks like. So we have a declaration list, and remember, a declaration list always has, either has a declaration. So yeah, one of the, let me just draw this out first, and then I'll I can't walk and chew gum at the same time. So I'm constructing the syntax tree basically in the same way that a parser would construct the syntax tree. In this case, starting from the root node. And notice here that because I'm applying this declaration list rule at each step of this syntax tree, hopefully this makes sense here, where a declaration list is composed of a declaration followed by another declaration list. And so for the root declaration list, this declaration, it corresponds to this int x, semicolon in our input. Is that clear with everyone, like why this declaration matches declaration in the input? We'll see the actual syntax of it, but just realize that this declaration maps to one complete declaration in our input. But remember, our rule says it's a declaration followed by a declaration list. And so this declaration list recursively has this same structure where it's a declaration followed by a declaration list. But remember, this declaration is a different declaration, the next declaration in our input. And the declaration list, even though the name of it is self-referential, in the actual syntax tree, it's referring to a different list, just like in a linked list. The linked list specification is a self-referential type, but in an actual linked list instance, that next linked list is a different instance of the list. Yeah, so somebody's already getting to the question here. So now we've got a declaration list here, because by the rule of a declaration list, a declaration must be followed by a list. But we've run out of declarations in our input. So instead, we have a special rule that matches the empty string. So this is why just in comments, I wrote the empty string, but that's just a comment. This rule here is really saying a declaration list can match the empty string. And so this epsilon here, well, I shouldn't even use this right now. So this is like in the formal math, they use the epsilon to mean empty string. So how do you represent an empty string? If an empty string contains nothing, how do you represent it? One way to do it in C would be double quotes for an empty string. But just like 0 is the absence of a count, an epsilon signifies the empty string, double quotes, 2 double quotes in C. And so this is why we have a rule in our grammar that where there is, there's really literally just no terminals are needed in order to match, or no symbols are needed in order to match this rule. So here, this empty string is really a comment. So let me just take this out just to show you the empty rule. This is just the declaration list can either match nothing, no possible content from the input, or it can match a declaration followed by a declaration list. And this syntax tree captures the syntax tree, which is the grammar structure for a single input. I hope drives home this point, why we define the grammar this way and why we can define a list this way in our grammar. So somebody asks, I forgot this is kind of like a post-order binary tree. Ah, yeah, exactly. So this is the really strong connection between grammars, language grammars, and their specification, and recursion and trees. And to me, after wrapping my head around this, to me, this is a much more natural way to think about recursion versus, writing a recursive function in C. Writing a recursive function in C is no small feat. But thinking about a tree structure as some instance of that recursive function, to me, is a lot more natural, is just a little easier to understand. And this also drives home the specification of a recursive tree, or the specification of a linked list, versus the, that specification of every possible list versus one possible instance of that list. So this is this diagram here is one possible instance of a declaration list for this particular input program. Whereas the grammar rule is kind of like a type specification that specifies what all possible lists should look like, or can look like. Does that kind of make sense? This distinction between the specification of the list, the type specification of a linked list, versus a syntax tree, which is an actual instance of that list for a particular input program or a particular data structure in memory. So let's see, does this, so somebody asked, so to check if we're at the end, we just check if there's nothing. Yeah, exactly. And I'll go over the API of the actual data structure that we use for abstract syntax trees in Simple C. I've provided this to you. And yeah, we'll use null as the sentinel for ending it. In C, it's tough to get around using null, using a null value without having to jump through a lot of hoops constructing data structures. But in higher level language, null is, null is Tony Hoare's billion-dollar mistake, he famously said. Because null is a value in any possible type, it's very easy as a programmer to just kind of misuse or use null. Misuse null, because null also is it signifies a lot of things. It also means, null is a problem. So higher level languages use more sophisticated type systems to avoid having to use null. Anyway, take a programming languages course, and if you take like Dr. Levin's programming language course where they talk about Haskell, you'll see a data type declaration that actually looks very much like a grammar. You can define recursive data types in a very similar way to the way we define grammars, and and this will avoid having to use null. But for C, since we're using C, when we actually construct a data structure out of this tree, we're going to use null as the sentinel to mean empty string. Somebody mentions they sometimes forget that recursion is more than a programming thing. Yeah, I mean, recursion is it's a different model of computation. Our physical machines use, the random access memory layout. You use the machine model of a store, a random access store. That's the mental model we use when we program C. And pointers are the ability to use an address as a value to manipulate that store. Recursion is just another model of computation. It's not, I don't know if it's physically realizable. I guess it's actually a good question. I'm so used to the random access model that I'm not even aware of. I assume you might be able to make a physical machine that uses recursion somehow. But all of our physical machines use the kind of more closer to a Turing model, or the von Neumann architecture, where you've got just random access memory. But for certain algorithms, for certain programming problems, they're much more natural to think about in terms of recursion. And I suspect that part of the difficulty of reasoning about recursion is not so much that recursion is hard, but that recursion is hard to do in a store machine model, like in the C machine model. And so if we think in terms of trees and grammars, we can reason about recursive algorithms much more easily. And then once you get used to actually implementing them in a programming language, or in a programming language that makes recursion easier, like functional languages, then doing recursive problem solving is actually much easier. And in some cases, much easier than doing problem solving in C, in the C's machine model for certain problems. Okay, so we're past 2 minutes, so apologies for that. Let's take a break until 11:30, and once we come back, we'll look at simple C, and we'll look at how we actually, what we need to do to implement our first project. So anyway, take a break. Let's convene at 11:30. I'll stay here for 5 minutes to take questions that people might have, and then we'll start up again at 11:30.
Yes, hello, Professor.
Yeah.
So I came in about 40 minutes late, so I didn't see what this file was supposed to be named.
What file was supposed to be named?
I'm assuming we're supposed to copy what you were typing out with index, declaration list, and all that.
Oh no, you won't have to type that out.
Oh no, okay.
Yeah, go back and watch the cloud recording. I'm just going over grammars.
Okay.
So so there's no more copy of code in this course. I mean, you should never be copying code from others. Mm-hmm. But I'm going to provide you the files, and then you're going to hand implement everything from this point on. I mean, I'll do live coding in class, so you can use that to start your project.
Okay.
But yeah, this is not something to copy down.
I just wanted to make sure. Thank you.
No problem. So somebody asked an interesting question. What is the expected behavior of dividing by 0 in the homework? And I'm presuming you're talking about the toy compiler. Since we're just compiling, we haven't gone into a really strict formal definition of that toy compiler language. But since we're just translating to assembly, the kind of semantics of dividing by 0 is we're just adopting whatever the assembly language semantics are, which in turn is the behavior of the ISA definition, the instruction set architecture. So whatever the machine does when you divide by 0, that's the semantics of our toy compiler. So this problem of divide by 0 or other invalid math operations, the way architects design that is they will have special, just like in the same way when I urged you, when you're implementing software, you should think about every possible input, including those that are invalid. And you should think about every possible condition through a branch, even those that are error conditions, and make those error conditions explicit in the specification of the language, rather than letting your program just fail with a null pointer error, which is really just passing that on to the machine's handling of that error. You should also account for all error conditions in your specification. And so what machine designers did is when there's some input like divide by 0 that violates the ISA, they have hardware functionality for handling those errors. So these are called trapped errors. When you get a floating point exception or a seg fault, this is not like the machine breaking. This is the machine doing exactly what it is specified to do. And so we just get used to it as like, oh, I saw a seg fault, so that must mean my program is broken. But what's really going on is that the compiler is just translating your memory read operation, or in this case, your divide by 0 operation, into assembly code. And the architects have defined the meaning of that division to say, if you have a 0 as one of the operands, then we are going to terminate your program. Or actually, we're not going to terminate the program. What we're going to do is we're going to throw a hardware exception. And so the state of the machine, there's a well-defined state of the machine that it goes into, that the machine goes into when you have a divide by zero. And it's actually the operating system that catches this, throws an interrupt. You'll learn about this in operating systems. Throws an interrupt, and it's the operating system, the kernel, that catches this interrupt and then terminates the process and tells the user, gives a signal to the user that there was a hardware exception that happened. There was a hardware fault that happened. So it communicates that to you. It terminates the program and then communicates that to you through a signal. Your bash shell captures that signal and then prints out, either does a core dump or whatever you've instructed your software to how to handle that signal. In the case of seg faults or divide by zero, those just get printed to the user. Those signals get handled by just printing to the user an error message and terminating the program. So we haven't really, so by, in the same way that in your program, when you allow a seg fault to happen unexpectedly, what you've done is just, by not being explicit about how those errors should be handled, you've just passed that burden of specification onto another part of the computing stack. So by us not defining what happens with the divide by zero, we've just passed it along to how the assembly language and the machine, the actual processor, handles the meaning of that divide by zero. And it's the operating system that has all the plumbing to capture that hardware exception and pass it on to you, the user of that program. So yeah, there's no real free lunch when it comes to these specifications. It's just, we pass the buck onto another part of the computing platform. So from the programming point of view, divide by zeros are not handled by core dumping is absolutely expected behavior. It's defined by the operating system. It's not like some physical process that happens when you put a divide by zero in the machine. There's no physics behind that says, oh, a core dump happens. It's an explicit code that the kernel and operating system wrote to say, when the machine throws a hard divide by zero exception, I capture that. The kernel developers write handlers for each kind of exception that can happen in the hardware, and the code that they wrote to handle that at the kernel and the operating system software level is to say, well, if I get that, it's actually useful to the user to have a dump of memory so they can inspect for debugging purposes. And so they will just, that's explicitly done. That's not some law of nature that happens. That's some designer who wrote code to make that happen. From our level, we talked about abstractions in the first week. From our abstract level, we don't think about that implementation. We think, well, this is the natural behavior of our operating system. When we have a seg fault, we get a core dump. So if Josh or the graders are going to run a divide by zero, I'm not going to try to trick you with this kind of stuff, but that is the expected behavior. That's what C does too, right? That's what happens if you write a C program that has divide by zero. So C is also not specifying, well, they may specify it as undefined behavior. So which is a kind of catch-all that says, I, as the compiler writer, I'm not going to handle this. If you write it, you're on your own. You're on your own. It's kind of a non-specification. So undefined behavior is just explicitly saying, this input language is not supported by me. So just don't write that. So core dump, that's a good question. I don't know. It might be like a flag. How to get core dump on seg fault. Oh, it may not happen on a floating point. Floating point exception. This happens on seg faults, null pointer errors. How do you actually cause it to get a core dump? How to get a core dump? Okay, so I guess there's a tool where you can tell the kernel to turn on core dumps. You can tell it where to put the core dump. Because kernel wasn't writing a core dump. Where's my core dump? Yeah, so I guess there's some parameters to the kernel that you can provide to tell it where you want to put the core dump. But yeah, this is a feature explicitly developed, explicitly written into the kernel and the system software to to handle what happens when you try to, I mean, when a seg fault is really, you're trying to access memory in violation of hardware security protections. So there are protections at the, this is getting into OS, but at the hardware level, you know, decades ago, system builders realized that they want to separate the operating system functionality, which abstracts away access to the hardware, from user access to it, largely for security and reliability reasons. If you're a programmer and if you made a null pointer error and there were no hardware protections, you'd start overwriting the memory of the kernel and the system, and you'd get very unexpected behavior. I mean, likely crashes, and these days with security becoming, you know, more and more prevalent, it's also extremely useful to have hardware protections on security, so that even if there's a bug like in an application, you won't violate the security guarantees of you know, memory separation between processes. And so it's the kernel and the system software that is providing the definitions of the behavior of what happens when you have these hardware exceptions being thrown. You know, some of them are hardware exceptions that are based on the definition of math, like what happens with a divide by zero. Some of them are just software exceptions, like I don't want users to access this memory as a kernel writer, and so I'm going to tell the hardware to turn on these protections and then send me a signal when the application violates these protections. And this is becoming actually more sophisticated. These hardware protections are becoming more sophisticated with like Intel SGX, these secure, and AMD's, what's it called? I can't remember what it's called, AMD. But there are hardware protections to actually prevent even the kernel from accessing memory of applications. So for instance, in cloud computing, if you want to have some stronger guarantees that the data that cloud providers is operating on isn't being observable by the cloud service provider, there are now hardware protections that can help encrypt and try to ensure that the kernel itself, the operating system itself, can't even read the memory that's being operated on. This is also called an enclave, secure enclave. So Apple markets this a lot as their hardware protection. But this is something that's, you know, this is pretty old at this point. I think a decade or two old. And you know, the idea behind this is you know, before this was commercialized, these techniques were commercialized. This notion of using the hardware to enforce security protections has gone back quite a bit at this point. Oh, so Josh had a test case where the toy compiler had to divide by zero and got a core dump. That's odd. Okay, before we begin, I will be right back. Okay. Oops. So let's see. Oh, a bunch of questions here. me see if there's anything I should address. Yeah, so somebody's worried about like core dumps divide by 0, and they're talking about it. Don't worry about it as long as you're. So I did not like. I mean, it's a toy compiler. It's not. It doesn't have to. It doesn't have to like, gracefully handle divide by zeros and seg faults. I wouldn't worry about that. You really just need to copy it verbatim. If you're getting a seg fault. I wouldn't worry about it as long as you copy it verbatim and it works on the small number of examples that we've given. You should be fine. We're not going to do like extensive testing of it. It's really just to get you used to the system tooling that we're using for the project. All right. Oh yeah, getting a backtrace. That's also useful. We'll look at that. We'll look at that later. Okay, let's take a look at, yeah, exactly, building muscle memory, getting good at, getting fast at the command line. There's very little, there's like no intellectual involvement. It's just practice. It's like learning an instrument or learning, drilling in sports. It's really, yeah, it's just developing that muscle memory. Okay, so before the break, we gave a kind of intuitive introduction to grammars. And now let's take a look at Simple C's grammar. So I've provided this online. Actually, let's look at this in Emacs. Okay, let's go over, actually, yeah, I'll just go over the grammar first and then let's look more. There's a lot of symbols in this Bison form. There's a lot of kind of archaic detail to Bison files, and I'll go over that a little bit. You're not gonna actually have to write any of this. This is the file that I've given you for project 1, and I'll go over project 1 before the end of this lecture. But let's look at the grammar for Simple C. So I'm just going to walk through each construct we have in the grammar, and maybe it would be, let me actually, I'll show some quick examples of the grammar on the right here to kind of drive home some of the points. Okay, so a program is, as we talked about, is a declaration list followed by a function list followed by a main function. So what that means is if I've got a, I'm starting to forget the syntax of Simple C. So this is a function definition in Simple C. It's a little different from C. We'll look at that. But this is just saying that all global variables have to be declared first, and function definitions have to appear after that. And the last thing in the file must be a main method. So this is very different from C, where you can basically put these in any arbitrary order. In fact, main is not even required to be in a C program, as we saw with the toy compiler using separate compilation. The consequence of this syntactic construct is that this program here on the right, where I put a function definition first and then a global declaration followed by main, this would be illegal in Simple C. Let me also, yeah, this would be illegal in Simple C. Okay, so let me put this back in place. Let's look at the lists first. So the order of this is a little kind of backwards, but so a declaration list, as we saw, uses this kind of linked list structure where it's either an empty list or a declaration followed by another declaration list. That's the exact same list structure that we looked at. So somebody said it looks like Haskell. Yeah, I kind of stole some of the type specification. I think it's a little more explicit than C's type specifiers are a massive pain. Okay, so that's a declaration list, then it's followed by a function list, which looks exactly the same, just another kind of linked list of functions, and then followed by a main function. So a main function in C is a main keyword. By convention, we use capitals for terminals or tokens in the language, followed by a left brace. So this is this is how we can define a token by its string directly. So we can use these single quotes to just say, well, this terminal is a single character in the input. It's just a little simple trick in Bison. So these quotes kind of say that, okay, this is not, this is part of the source language that we're processing. And a main function inside of it can also have a declaration list followed by a statement list, followed by a return keyword, followed by an expression, followed by a semicolon, and lastly, a end curly brace. So this is a bit of a long one, so I'm going to let you sit and digest this for a second and write some code here. And I'll see if you can answer some questions about this code. So while you're looking at it, can anyone tell me whether this code on the right here is valid syntactically, simple C or not? So this is certainly valid C, but is this valid simple C? I'll give everybody a second to digest this while I invalid because of the redeclaration. Ooh, that's a good one. So redeclaration is a type, so something that we can't capture in, even if this were Y. Let's not think about this now. Yeah, so we're just talking about syntax here. So yeah, as we'll see with type checking, we can't capture these type notions with the context-free grammar. So syntactically, somebody pointed this out because this declaration, and even before thinking about the usage of the symbols, the placement of the declaration is not permitted by our grammar specification after a statement. So x equals 2 is a statement. I haven't really talked about statements, but it looks like C basically. It's because this declaration appears after the statement. But in our grammar specification, there's only one possible specification for the syntax of a main function, and that's the one where a declaration list is first and a statement list is after the declaration list. So by putting a declaration list after the statement list, this program won't even parse because it violates our syntax definition. Let me see if can't remember if okay, good. I've got I'm gonna have to change that a bit. Oh, sorry, I'm talking to myself. I want to show the actual project one running by the end of this lecture. Okay, so good. So this grammar specification, so this is exactly what syntax does. It provides restrictions on the legal orderings of tokens in the input language. So somebody asked, why does it take return as a parameter? So firstly, what do you mean by it? Are you talking about the right side or the left side? So here, the main function, either or. Okay, so this is where this distinction between the meta language and instances of the language is really, we really got to make a sharp distinction of this in our heads, because this gets really confusing really, really quickly. So on the right-hand side here, we have one instance of the simple C language. And on the left-hand side, we have a schema or a grammar that defines what all possible input programs can look like. And so this specification on the left here is not a description of what one simple C program will look like. It's a schema that defines the syntax of any possible input program. So this return statement here is not a parameter to anything. It's just a list of symbols that define what possible symbols can appear in any main function. Does that kind of, it's a really tricky thing to describe, because I also have to use language to describe the description of language. So this, this becomes just a meta recursive, expletive here, cluster expletive. It's very tricky to kind of wrap your head around, because we reason using symbols and we communicate using symbols. So just try to describe the language itself using symbols becomes really tricky. So on the right, yeah, these are also not parameters. And in fact, the meaning of this language, I'm sort of hijacking your understanding of C in order to talk about simple C right now. But strictly speaking, the meaning of this language is not defined until we have the left-hand side and the compiler to define the semantics of this. So there is no real meaning to these on the right. And in fact, if you look in my editor, I just have a scratch buffer open. There's, doesn't even have an extension. There's nothing in the machine that says that this is a simple C program. This is just ASCII characters in a text file. With the tricky part about reasoning about this is that we can process languages so instantly and unconsciously that as C programmers, we'll look at this and say, well, okay, this looks like C. I'm already interpreting the semantics of this. But when we're trying to write a program that is processing this language, on the left-hand side, we have to be ultra precise about what the meaning or what the syntax of this language is, the specification of this language in the first place.
So on the left then, is there two separate declarations of the function body, or is the one where we have the declaration list, statement list, return expression, is that parameters or is that the body? Because I'm just confused, because I assume that the to-do portion, I assume that was the function.
Oh, I'm sorry. Ignore this for now. Ignore the to-do for now.
Oh, okay. So this
is going to get quickly going to get confusing. So this is not the body. This what's highlighted here on the left, the grammar construct. This is not the body. This is not the body of a main method. This is a description of the syntax of what every main method must look like. So it's just
so like a blueprint though for a function body.
Yeah, like a blueprint or a schema. This is like this is a blueprint for what main methods must look like. And so the notion of a body is something that we define in terms of the language. So by body in C languages, we mean the stuff inside of curly braces, right? That's what we mean by body. And by parameters, we mean the arguments passed to a function. But we haven't even defined yet the syntax of the language, much less defined what parameters mean. So we're just, it takes a little bit of kind of almost like introspection or navel gazing to think about this, because we use language so fluidly that it's hard to step back and start reasoning about just the symbols themselves detached from their meaning. So somebody's bringing up a really good point here. Int X, yeah. So if we look at the declaration specification, there's no commas as terminals in this language at all, much less a structure that allows you, a grammar specification that allows you to express something like this in the language. That's a really good point. There is no, this would be a parse error in simple C. So let's see, somebody is asking, okay, so good, that clears up the function body stuff. So even the notion, we really have to in our minds, detach the symbol from the things that the symbols represent. And now we're writing a program that is kind of automatically processing and interpreting the meaning of these symbols. Because truly, at the machine level, the stuff on the right here in my Emacs buffer, these are just being represented in memory as just numbers that have corresponding ASCII codes that the Emacs program is telling the video functionality, video hardware, to draw as symbols that I, as a human understand. We understand these symbols. But this is so unconscious to humans that it's very hard to detach our own processing of the language from what a machine does to process the language, from writing code that processes the language. So yeah, I really want to like get this across, this notion of the meta language versus the language itself, and this distinction between the symbol and what the symbol represents. This is also a popular thing in philosophy, you know, the finger pointing at the moon versus the moon itself. You know, there's like some, you know, philosophical aspect to this as well. But yeah, in computing, this becomes real in computing, where we actually have a physical representation of the symbol itself. And so now we have to separate the symbol that represents the symbol representing the symbol. Okay, so somebody's asking how we would make commas valid in simple C. I'll leave this as a bonus exercise. If somebody wants to support new constructs, so I'll talk about this later when I talk about more, you know, language implementation. But you would just, so how would we do this? So somebody want to answer this? How would we make commas valid? So how would we allow constructs? How would we make how would we allow this to be valid in our simple C syntax? Does somebody want to try to like, see if they want to venture a guess? Or does somebody know? By adding commas into the main description. Okay. So if I could say like, well, okay, you can have a comma here. Well, what would that mean? Okay, so somebody said commas between statements. And somebody else said commas as an option to the declaration list definitions. Yeah, so you're sort of circling the, zeroing in here. So declaration list is the symbol that captures all of the structure of what this stuff looks like, of what declarations look like. So the change must happen in the definition of this symbol. So this is the kind of beauty of this syntax, of these grammar definitions, and also what makes this a little tricky. Because here in our main function, we have a mix of terminals, that is tokens from the actual input, a mix of those. So there's definitely a main keyword in our actual program, and there's definitely a left brace in our actual input program. But there's certainly nothing that says declaration list our input. And so these grammar constructs are hierarchically specified. A main function has to have a main keyword followed by an actual L brace symbol, but then the stuff that follows those tokens is specified by some other non-terminal, by some other grammar construct. And so to actually know whether this is a valid input, we need to look at this nesting relationship kind of recursively, or think of it as like recursive or following the tree or calling another function. We have to go look at this specification of what a declaration list is. And here's our declaration list. Our declaration list is either an empty string for reasons that we saw in the syntax tree example that we did in the first half, or it can be a declaration followed by a declaration list. And so here, here we also don't want to add commas because we have to look at what a declaration is. A declaration, it ends in a semicolon. So that would mean the commas would appear after declarations. Instead, we'd have to modify what a declaration is to allow lists of names in order to add them. So somebody's asking, would adding commas to the specification make them necessary? That's a good question. So if I added commas to the specification, I'll ask it to the class. If I add commas to the specification, let's say I just add it here. Let's say I add this to my grammar. Would a comma be necessary in that case? Yes, a comma would be required. So would there be a way, and so in C, you can have an arbitrarily long, arbitrary number of declarators in your declaration. So how would you capture that notion of an arbitrarily long number of identifiers in your declaration? So some recursive way, yeah, making stuff optional. So they're not statements. Statements is a particular symbol in our language. So good, somebody's saying making an identifier list. And there's kind of a hint up here where we do have commas. I forgot, we do have commas in our language. We don't have commas around declarators though. But yeah, so somebody's saying make a list. So exactly right. So if we want to capture this notion of an arbitrarily long input, and we want to capture it in a finite grammar specification, we can use this self-referential grammar constructs. This is where, this is like a schema for recursion. If you think of, you can really conceive of like a Fibonacci recursive implementation or tree walking as a kind of grammar that you're writing, in a sense. And for some problems, they actually are equivalent. But it's this notion of capturing infinite or arbitrarily large data structures or instances or inputs, capturing them with a finite definition. So I'll talk about more recursion later when we go over tree walking. But you could imagine writing a function that says, this is the Fibonacci of 5, and you have one function for defining Fibonacci of 5, and that calls another function called Fibonacci 4, which calls another function Fibonacci 3. You could have 5 functions that you write, avoid any kind of recursion. But you need as many Fibonacci functions as there are the size of the input, or have to correspond to the size of the input. So recursion is a way to have a finite definition to express recursion over arbitrarily large inputs. And so, yeah, so people in the chat are talking about identifier, comma, identifier list. That's exactly right. It would look just like typed list. And it would be fairly easy to implement. You'd have to capture you'd have to capture that here in the declaration, where you say, instead of an identifier, this is a identifier list. But yeah, that's it. This is a nice little aside. This is a really good aside from everyone. So yeah, thanks for that question. It's a good question. Let me make sure I didn't leave anything in here. Okay, good. Were there any questions that I missed while I was blabbering on? Other questions about this so far? Okay, so main function. Okay, so another thing here is one feature of simple C that's different from C is that a return statement is not actually a statement in our language. It's a part of the syntax of main. And as we'll see with functions, it's actually a part of the syntax of functions. So the reason for this, just like you all noticed that without having alternations, without having a pipe to do alternate rules, it's basically a mandatory syntax for that grammar construct. And so by forcing the return to be inside at the end of functions, this will actually make code generation a little easier, because if you have multiple places where you can return, it makes code generation a little bit trickier. So simple C, all functions have to have the return at the end. You have to put the return at the end. And this also means that there are no void functions in simple C. Every function has to have a return value. But a void function, you can semantically have a void function by just not using its return value. And voila, you've got a void function. And in fact, void functions were not in the original C specification, if I'm remembering right. Void was added later as a type. Maybe in the 80s or 90s, I don't remember. Okay, so that's the main function. So function list, hopefully by now you're used to at least seeing this. Function is very much like main. So in C, main functions are optional because you can have separate compilation. Yeah, C is still being updated. So C, 2011, there was a lot of updates to C. Syntax idea, yeah. So all these languages, so just like a human language grows naturally, unlike what grammar authoritarians like to believe, languages are, if you think of humans as a kind of naturally occurring animal, languages are a naturally evolving thing. In the same way that if you go back and read Old English text from like 500 years ago, they'll be barely comprehensible, but perfectly grammatically and semantically correct. For those speakers at that time, the language is always evolving. And even though computer languages don't really have the same kind of natural usage that human languages have. There are at least standards body. Well, so the thing is, you could certainly have a situation where everyone writes their own C compiler, which was kind of the case a couple decades ago. Your program may behave differently with different compilers. Standards bodies have tried to incorporate new ideas about the language into the language and advance the language. And this may be syntax changes, semantic changes, defining behavior, defining how the compiler should treat things like divide by zero. Should there be a built-in checking for that? And so in GCC, you can actually turn on different standards and different levels of checking, different warning levels. There's a pedantic mode, which will give you more warnings. There's a mode where you can say, I want the 1999 version of C. I want the GCC version of C. I want the 2011 version of C. And so, like human languages, these languages are evolved. I mean, they're evolved consciously using design decisions, but they're evolved, like languages. And in the same way that humans find more convenient expressions, more convenient idioms, or just part of the culture learn idioms, these can be incorporated into the language. And in fact, in some sense, you can think of programming languages as providing a platform for defining your own idioms. When you define a function, we'll see when we implement the language, you're in a sense extending the language. You're defining a new symbol to have a meaning in that language. So if you try to call a function without defining it, you get this undefined symbol error. But if you define it, then any program that uses that library can then use that symbol. That's in a sense adding a new word to the language. So if you watch that Guy Steele talk about growing a language, he gives a very great overview of that notion of programming as building a new language. Yeah, and so somebody said slang can become real. So of course, yeah. So slang is like slang is like an illustration of kind of like spontaneously emerging terminology and phrasing that have not been, what is the difference between official language and slang? I mean, there's no difference. It's just the official language has been written down somewhere, or some body of people decide that their dialect is the official language, right? And so if you read like Merriam-Webster's, they have, if you're kind of a nerd about this like language stuff, dictionary, lexicographers is their formal word. They're not defining the language. They are just describing it. They're like observational. And so they make decisions about when to include words in the language and how to define them. And so they just look at real world cases like, okay, did thousands of people start using this word? They'll often use literature and publications because, they're literary. They're looking at like they're not an auditory dictionary. They're a written dictionary. So they'll use written sources often. But spoken sources, nowadays spoken sources are just transcribed automatically, so they become written sources. But you'll notice, there's really good blog posts on Merriam-Webster about like, there are some grammar authoritarians will say like, I can't say if I tell you to try and program project 1, some grammar authoritarian might say try to program must be what you say. But in fact, if you look at like literary history, there's earlier cases of try and versus try to, and the number of lexicographers will look at the incidence of these in literature, or they'll look at famous books like F. Scott Fitzgerald's writing, and they'll say like, well, they actually use this usage. So how can you say that it must be used this way? It's difficult to claim that is actually a part of language versus a part of enforcement of language. And so this becomes a little tricky in grammars, because in grammars we're writing the specification, and so from a programming point of view, we are enforcing the meaning of that language. And this is useful for programming because we want to have agreement across all of our system tools about what the language means. So it's useful to have these standards, but there are approaches nowadays of combining natural language processing with programming and trying to have a way to automate the process of programming using natural language. Of course, this also brings in the problem of the ambiguity in human language and the fact that it changes over time. So if you want to be able to run software from 10 years ago and you don't understand the new slang, or even worse, words change their meaning over time in how they're used. So for instance, the word animus comes from the Latin word for spirit, and was used like that originally as it was imported from language. But animus now has a much more specific meaning to just mean bad spirit or bad feelings about someone. Okay, so anyway, so aside on like language, I'm not a linguist, so take what I say with a grain of salt. Go read the lexicographers and experts on linguistics about this. But this is what I've just sort of observed from studying this from the compiler point of view. Okay. Okay, so functions, yeah, in simple C, so all these syntactic restrictions, they may be a little annoying when you're trying to write simple C, but these are going to be your friend when you're generating code. This makes it much easier to generate assembly from this, because there are just fewer constructs that we have to define the meaning of. Okay, so functions are quite different from C in many ways. So we can see it here in the grammar definition. So unlike C, where functions look a lot like variable declarations for lots of various reasons, and in C, function declarations can be separated from function definitions. In our language, and that's because of the need for C to work in a single pass. We'll see this in type checking, why declarations and definitions are separate in C. But in our language, the way a function is defined is instead we put the name of the function first. We don't put the type first, put the name of the function first, and then a list of parameter names. So here, this parameter list, which is defined here, actually here's an identifier list, which we could use, has the same structure as declaration list. Even though it has the same structure, I wouldn't use the same name because it's a different grammar construct that happens to have the same structure. It's an identifier, just a list of identifiers. So no type information is put with, yeah, somebody noticed my syntax error already, very good. So no type information is provided in the name of the function and its parameters. This is very much like actually old school C, KNR C, Kernighan and Ritchie C, where they actually separated, just like this, they separated the symbols for the name function and its parameters from the types to some degree. I mean, the syntax was different, but they also separated parameter types from parameter names. And that's because these as we'll see when we see how functions are implemented, these parameters are actually also double as local variables to the function. We'll see this when we talk about typing and scopes. But so for the syntax, we define the naming as a separate construct. And then we have a colon, which is kind of stolen from Haskell and other functional languages. And then we have the function specification after that colon. So I'll go into this functional specification. Did we talk about this? Arrows for return values? Did we talk about this yet? I can't remember. I feel like we talked about that. I can't remember if I talked about this with the TAs or in class. And then just like in C, we have a curly braces to identify the body. So somebody noticed already, one of your fellow students talked about I was missing a colon in my input program, and they got this by looking at the syntax specification. So the syntax specification says, after your name of your function and your parameter list, you must have a semicolon, and that is followed by a type. And now notice something a little interesting here, that in my grammar construct, I have my grammar specification, I have a single construct for all type specifiers. So I don't enforce what type this function should be at the syntax level. This makes the grammar actually a little easier to write and the AST a little easier to build. Instead, I just say, well, okay, I don't care what type it is from the syntax level, it just has to be some type construct. And then just like in main, the main body, this is identical to the main's body. The only difference between main and a function is the stuff before the body of the function. So you could certainly try to re-engineer this grammar and combine things, but I didn't do any of that. I tried to optimize making this easy to write the compiler. Okay, let's take a look at types. So apparently I did cover this a little bit, but let's look at all the way types can be specified in our grammar. And this will be kind of interesting because in formal type theory, the kinds of types you can have are actually often defined using a grammar. So this is a grammar that defines all the different types we can have in our language. So let me show some examples of this first. So in C, the kind of unfortunate part of C is that the type specifier and the specification of arrays and pointers are actually part of separate grammar constructs. I'm doing some C processing in my research, and it's a massive pain to deal with this. So when I was looking at simple C, I realized that we could greatly simplify the specification of types by using something like what functional languages in Haskell does. So in C, this int is part of a completely different grammar construct from this identifier name. And in fact, the pointers and array specifications are part of the grammar that it specifies the name of the symbol, which is just royally confusing. So in simple C, whether we're specifying a pointer or an array or even a function is all captured by the syntax of the type specifier. So if I want to specify that X is a pointer to integers, I basically stole this kind of either Java generics or Haskell style specification of types. So we'll get to the meaning of this later, but this is equivalent to saying int star X in C. By the way, this also has ambiguity with multiplication if type def. So if Y is a type def, if I say Y star X, you can't distinguish that in a context-free grammar from multiplication. So it's massive pain. Anyway, okay. So is this unclear to anyone? This notion of constructing a type with this syntax, where I say pointer brackets int. Is this like still confusing or weird to anyone? It's just equivalent to this. And similarly, arrays are specified like this. Now, those of you who are familiar with C programming will probably notice that in C, I can declare arrays without specifying the size. And in C, you can even specify arrays using what look like variable size arrays. Now, to make compilation easier, I'm first of all not allowing expressions inside of array sizes. They're a pain to handle at code generation time. But I'm also making this very clear distinction between arrays which are fixed size versus arrays which are variable size, or at least arrays which are heap allocated. So heap allocated arrays in C, if I define this, they have to be specified using malloc. So in C, this is really just syntactic sugar for a pointer to an int. There's really no difference from the machine level between these two declarations. And we'll see this when we actually implement arrays and pointers, that arrays and pointers are largely the same thing in C, except if you have a stack allocated array of a fixed size, the way it gets represented in memory or way it gets handled in memory by the compiler is different. But anyway, this is how you declare arrays. They're only for fixed size arrays, and you have to specify an integer constant. You can't specify an expression. And then functions, I talked about this a little before apparently, but a function, the syntax of a function is a list of other types, and it's surrounded by parentheses, followed by an arrow, followed by some other type. So, okay, so let me put a really complicated example here. And ask you whether, okay, this is devious enough. So here is here's some syntax of a type declaration in simple C. And my question to you is, firstly, is this valid simple C according to the type grammar construct? It's a slightly tricky question. Can you assume parentheses are defined? Well, parentheses are terminals here that are specified in the Bison grammar. So parentheses are just symbols that are consumed from the ASCII code. Sorry, so I made this ultra confusing because yeah, okay, let me make this a function definition just to reduce a little confusion. Well, let's just say we have this type specifier so separate it from, just look at this type construct by itself. Is this a valid, does this match my grammar construct here? Let's forget about it in the context of other constructs. So forget about it being inside of a function. Just think, does it match the type grammar construct I have here on the left? Does this syntax on the right? So somebody says it looks like it matches the 5th definition for type. So they're saying it matches this one. Okay. So, ooh, maybe I should do well, okay. I'm not going to belabor this too much, but yes, it matches it. I have parentheses around the type. So let me try to break this down a little bit without having to do a syntax tree for this. Actually, let me run this through the parser so you can see the syntax tree of this. Let me first turn off type checking. So this is, so let me make I'm going to declare a variable to be of this type. I need a main method. So here should be a complete simple C program. And hopefully, if I didn't mess something up, syntax error. So somebody said I had oh, okay, that's what you were saying. Thank you. I did not understand what you were saying. Wait a minute. It's not working. What did I mess up here? Oh, I forgot a keyword. So my syntax here says I have to use the function keyword. So it is in the parentheses, well, and we'll see why in a second. I think, is that right? Wow, oh, yeah, sorry. I'm sorry. I'm sorry for making this confusing. I'm confusing my own syntax. All right, yeah, you're right. So you had the parentheses around the type, which is not valid. So I forgot that I need to put this function keyword in order to, just like pointer, I need to use the function keyword to identify when I'm using a function type. So my question was, yeah, so sorry about that. Sorry for the confusion. So this is, yeah, so function has to be, the function keyword has to appear before the parentheses that are listing the types of the parameters. But my question, so okay, but it's the same question. So is this a syntactically valid type? And I already ran simple C, so you saw that it's syntactically valid. And so somebody said this matches production 5 here. And so why does it match? So we have, the function keyword here, which corresponds to this. We have the parentheses and a type parenthesis list, and we have an arrow. We have a type of yeah. So this type here, once we're past the arrow, this grammar construct is saying, well, now we have to have a type as the last thing. But remember that type can also be a function type. So this entire highlighted portion here matches this type symbol here. So we have this kind of recursive nesting of function types. And so the question is, what is the meaning here? Is this passing a function as a parameter? What does this mean? So we haven't actually defined the meaning of this. And in fact, in simple C, we're not going to allow this kind of thing. But in functional languages, this is saying that we have a function that takes two parameters and returns a function. So in functional languages, functions are also values. You can return functions as values, just like you returned an integer value. So take programming languages, learn about functional languages. We won't get into that. But this type specification in functional languages is actually valid and supported because they allow you to create functions that, or they allow you to write functions that actually return functions themselves as return values. And so I think understanding, kind of some of this programming language design aspects helps a little bit, I think, to understand functional languages and what they add, the kind of constructs that they add. But anyway, I just want to show that as a little exercise in syntax, because we haven't defined the meaning of this, remember. We haven't defined the meaning. So we've just said that it's syntactically valid. Yeah, so somebody points out that C does have function pointers, and that's absolutely right. So C has function pointers, and so the, so maybe it's a difference in the type, or what, it depends on what you mean by returning a function. So C has pointers, so you can return a pointer to anything. And it allows you to dereference pointers. So when you dereference a pointer and then call it as a function, that's effectively like returning a function as a value. But the difference in Haskell and functional languages is that it's actually supported in a type system. You can actually do like type checking on functions. You can also return partial functions. So anyway, take a programming languages on this. So there are some kind of language design differences on this that kind of like object orientation adds objects to the language constructs themselves. And you can simulate that using structs like we do for the AST. So with first class functions in C, so it's first class means that it's part of the language constructs themselves versus something that you can implement in that language. Anyway, take a programming language, take the programming language courses, particularly Dr. Levin's course will go into Haskell and talk a lot about these high-level functional programming language concepts. So anyway, I just wanted to check to see whether you guys think that this is syntactically valid, and it is syntactically valid. The interpretation of it is something that we'll leave till later when we actually implement what these constructs mean in terms of assembly code. But for now, the syntax allows this kind of type specification. And as we can see in our grammar construct, I'll go over the AST in a little bit later, but it actually, our parser supports this and generates a syntax tree for it. Okay, so statements. Other questions on this? I want to make sure that I get to everything that I want to get to today. Yeah, I think we're good so far. So somebody says it's hard to read because the caps are on the right and not on the, it's all caps on the left here. So, these are actually on the right. So recall that this is equivalent to saying this. Yeah, maybe it's a good time to reiterate this, but this is equivalent. This is just Bison's syntactic sugar for, these three are equivalent to these three. That pipe is basically just saying, and so int, okay, so yeah, so remember int, the int, yeah, this is really tricky when we're talking about meta languages or languages. So on my right side here, on my, in my type.simplec browser here, is that what maybe, is that what you meant? Because on the right in my, okay. Yeah. So remember on the right side here, this is an editor. This is a file editor where you have the literal ASCII codes for int. Oh my God. a little, yes, so all labs are recorded. I hope your cat is okay, is going to be okay. That is, geez, okay. Yeah, all labs are recorded. I hope your cat is okay. This is going to be, for people who did not read the chat, this is going to be an ultra confusing part of the lecture. Yes, labs are recorded. Yeah, so on the right side, or on the right-hand side here, remember, type.simplec is this is my editor presenting me a file that has the literal ASCII codes represented as machine integers, literal ASCII code for the letters INT. And so it's lowercase because it's using the ASCII codes for the lowercase letters. On the right-hand side here, remember, this is, oh yeah, I see. So this is a symbol that represents the ASCII code for all three characters, all three characters together at the same time. So this is not, this INT here is a symbol that represents the terminal, which is represented in the input language as three characters together. So the reason that we have quotes here for less than sign is because these are for single characters. But when we have multiple characters together, the lexer is giving us a single token as the output, not three tokens. So on the right-hand side here, there's three symbols to represent INT. On the left-hand side here, there is one symbol to represent INT. But because we need to actually represent that symbol in Bison, yeah, I mean, we could have written this using any symbols we want, but just from the grammar point of view, this is a single symbol in the grammar. Yeah, they're just capitalized by convention, and yeah, I see that it is confusing to use the same ASCII characters for the grammar symbol versus what the input language will actually look like, but realize that in ASCII code, these are actually different encodings. These are different codes. And yeah, so I think, keep in mind that this is the grammar symbol for the INT terminal. And on the right-hand side, these are just three separate characters in the input program. Yeah, there's going to be a lot of, this is why I wanted to kind of go through this intuitively and have you write the toy compiler and have you use Bison, because this is the really kind of, it's like almost so simple that it's hard to like wrap our heads around, because the representations of these are all just, machine integers. And so it's our software that we write that interprets these symbols that make it like real to us, or that satisfy the abstraction that we use for it. So yeah, so anyway, all the stuff in the Bison specification are the symbols that represent our grammar, plus a little extra syntax in the colon and the semicolon for the Bison specification itself. Yeah, so you're gonna have to like reason about different meanings of the same symbol all over the place here, and just always keep in mind the moon versus the finger pointing at the moon. If you like remember that, like Chuan Zen Buddhist thing, that's what's going on here in compilers, and it's all over the place in compilers. Okay, so I'll let you read through the rest of this. So let's get into what the actual project is. So the project, I've given you a really long time to do the project. Like, I think it's like 3 weeks or 4 weeks. So the assignment is now posted as project 1 in web courses, but remember, for the 4 projects, those are all submitted on oh, my accent is going back to I'm reverting to my childhood accent. The project is on GitHub. You submit it all on GitHub. And so you really just, the link is already provided. You've already provided us the link to your project as your first assignment. So there's nothing to submit for this web courses assignment, but it still has a due date. And we're going to enforce that due date by checking, just cloning your repositories after the due date. Yeah, so for homeworks, yeah, let me, yeah, so I made this is my being, precise, like in languages, I named the types of assignments 3 different things. So I'm using this notion of, well-defined symbols. So projects are the things that are submitted on GitHub, and those would be 4 projects for the Simple C compiler. The homeworks, these are handwritten, or you can type them up. These are submitted from GitHub. No, so there's nothing to submit in web courses for the 4 projects. You've already submitted your repository. We are using version control to manage your submission. So we'll know through the log, and we'll know because we're going to clone your repositories right after the deadline. And there's no way to resubmit it after the deadline. If you resubmit it after the deadline, you can't do it without going back in time. You can edit the logs. I'm not going to show you how to do that. You can edit the logs, but we're going to just clone it. And whatever we have cloned at that time period is your submission from GitHub. So yeah, if you want to resubmit, just push to GitHub, and be sure that you're using that same. So Josh sent out that instructions on just clone a fresh copy of your repository and run. This is just do what we do to grade your scripts. You can do it yourself. So there should be no surprises in grading. It's fully automated. It will be fully automated, and you'll eventually, the scripts are still being developed, but you'll be able to just run the scripts. You'll be able to clone a fresh copy, run the scripts, and grade yourself. Okay. So somebody asked if they want to work beyond the code. Sure. As long as it's backwards compatible with our. So this problem of having multiple digit numbers is solved in the Simple C already for you in the lecture. So if by all means, if you want to exercise and practice, go for it. As long as it's backwards compatible with Toy compiler, like it extends the language, and our grading scripts work, it should be fine. Yeah, by all means, but there's no need to do it for today for that. This is already done in the Simple C lecture for you. Okay, so there's the grammar. Let me show. Might as well show the lecture real quick. So I wanted to kind of avoid you having to deal with this, but the lecture is kind of the same idea, except instead of a grammar, we use regular expressions. Regular expressions match sequences of characters. We're going to go over this next time, kind of from a theoretical point of view. But basically, all this is doing is saying, if I see these 4 characters in the input, if I see these 4 characters in the input, then return to the parser, return this token. So this, for those of you who are confused about why it's lowercase int on the right and uppercase on the left, the lexer is actually what's linking these 2 together. So on the left, we have a representation of the ASCII characters in the input. And on the right, we have a snippet of code that says, once you see those 3 characters in the input, return the integer, return the int token. So this int is a symbol that returns it. So yeah, this is, I probably should have shown this before, but this is the connection between the raw ASCII bytes and the tokens, the terminals that the parser sees. And so I don't have too much time to go into this in much detail, but the parser is what defines the tokens. And then the lexer is, basically reports those tokens back to the parser, just like we did in the toy compiler. Yes. Yeah. Let me. Oh, this lecture clicked more. Okay, that's good to hear. I was a little worried about this one because this is getting into a lot of the nitty gritty. So let me go into the Bison specification now, so we can see how all the kind of plumbing behind specifying the terminals and non-terminals happens. So like I talked about with parser generators, let me show that really quick here. So recall that my point was that this parser.y file is basically just like a C file with a little special section inside that Bison uses to generate C code, so that our parser will just end up being, one C program, one C library. And Bison just uses these special archaic symbols to say, here is where you put C code. And so this C code here is just copied into the output file. So let me actually show you the output file here. there's going to be a ton. As you can see, this is a 2,000 line program generated from a 200 line program. But we can actually see what's just copied verbatim by Bison. You can see here's the part that's just copied verbatim by Bison. And so that's just in between these special characters here. The next part in this file is the token specification. So yeah, sorry I didn't make this clear before, but this is good to see now. This is actually defining the terminals of the language. So Bison, you define the user of Bison defines every possible symbol in the language, or every possible symbol in the grammar definition. So here are the tokens of the language. And now Bison also allows you to put characters in quotes. So you don't have to define them here explicitly as tokens. They just get reported like so. They just get returned as their raw ASCII code. Basically, it's saying just use the ASCII code as the symbol for that token. So it's a little hack for single character tokens. If you have a single character token, Bison and Lex will just use the ASCII code for it. It's a little kind of trick. But yeah, so in general, you define the tokens here with these special, with this special keyword in Bison. So here's all our tokens. I'll talk about these values. These are defining the types of them, but let's talk about them in a second. Here's the starting symbol. So one astute watcher pointed out that context-free grammars also have to have a starting symbol. So this is defining what the starting symbol is. We'll talk about this when we talk about grammars, but this is defining the associativity of lists of things, but we'll talk about that later. We'll also talk about this later when we talk about grammars. So don't worry about that now. Okay. So this is defining the types of every non-terminal in the language. So in order to understand why we do that, let me introduce abstract syntax trees. So we saw syntax trees here, where the syntax trees is basically the derivation of each construct in the language for an input language from its grammar. And I just spilled my water and my mouse is not working and I'm dropping things. Okay, now my mouse works. Oh, that's a mess. Okay. Okay, so this is the syntax tree. The abstract syntax tree is something that's used in the compiler world to, okay, I guess F means fail, is that right? Or do I get an F for this lecture? Oh, to pay respect. Oh, I did not know that. Okay. Give me 1 second. Oh yeah, slang in practice and language that I don't understand. Yeah, I mean, F can mean lots of, I mean, F is just one character, so it can mean lots of things depending on symbol, including some, inappropriate things. Okay, so abstract syntax trees are something that the compiler uses to represent the language as a tree, but it's more of like a design issue. It's more of a design convenience. So in order to compile the language into assembly, there's really no need to store things like there was a semicolon here, there are parentheses here. That's all captured in the structure of the tree. So abstract syntax trees, it really depends on the application that you're using it for. So for compiled languages, the abstract syntax tree will just omit things like punctuation. They'll use maybe better data structures like a linked list. If you have a standard library for linked lists, the abstract syntax tree might use that instead of having to use a tree node. And also may do some conversion of data types. So those integer constants might be turned into machine integers with A to I, for instance. And this is all very much like a design question. This is like an abstraction question. And as we learned a couple weeks ago, abstractions are designed based on how they're going to be used. So in a compiler, we preserve just enough of the structure and information about the input program So we can do error reporting and code generation. We never really need to use the semicolon again, for instance, once we've read it. For other tools, that might not be the right abstraction to use. So refactoring tools or IDEs for doing syntax highlighting, or rewriting tools where we're doing source-to-source transformation, which is what refactoring tools do, we may actually want to retain all the tokens from the input, like semicolons, so that we can rewrite them out again, or pretty printers have to do this. Okay, so the main thing here is that Bison, it's part so what Bison gives you is it just gives you something that will recognize, enforce the syntax on the input language, but it's not going to give you a syntax tree. It's basically like, it's almost like a pattern matching. It just says, okay, this program that you gave me actually matches the input syntax, but it's not going to generate any data structure or any tree that represents that. Very bare bones. So the way we generate a tree, you know, we want this abstract syntax tree just like in the toy compiler, so we could walk through it and generate code. In Bison, it gives us all of the parsing functions or all of the recognition functions, but it doesn't give us the code for creating that abstract syntax tree. That's up to us, the programmer. So the way we use Bison to generate the abstract syntax tree is we use this feature called semantic actions. And for those of you who are asking about these to-dos here, these are how you specify semantic actions in Bison. So firstly, what are semantic actions? Semantic actions come from this notion of the separation of syntax and semantics. So if we can specify the syntax using these grammars, then the semantics we can specify separately as a bunch of rules and actions to take whenever we see a particular construct. Those were money signs, yeah. Those, the money signs are Bison syntax for this. So semantic actions define a little snippet of code to run whenever the parser matches a grammar rule. So for instance, where is my code here? So let me show the semantic action for program in simple C. What am I doing here? Come on. Okay. Actually, let me show main as well, because there's other issues here. So I'll just show. Okay, here is the semantic action for main that creates an abstract syntax tree node. So remember in the toy compiler, we had these create underscore node functions that constructed each node of the abstract syntax tree. Here, and we had to call those from our handwritten parser. In Bison, all we have to do is put these little curly braces and put a little snippet of C code in there that says what we want to run whenever we match that grammar construct in our input program. So in this case, so for instance, I could just say, print F, and I can pay respect by printing FF. I can print F, literally print F. I could write this in my, let me see if I can actually compile this. And so if I pass in, so I'm going to get a seg fault here, but oh, it didn't print. Oh, there it is. There it is. Sorry, it's printed. It's just so yeah. So you can see here that now I'm paying respects here after spilling my spilling my water. Yeah, so when it matched that that program construct, it just ran whatever code was in between these curly braces. It's basically, yeah, kind of like a function body. It's like a function body to a recursive, one of these recursive parsing functions. Now, in order to help create an abstract syntax tree, Bison also provides semantic values. That's what this double money sign means. So I'm paying my respect, and then getting paid. So these double money signs actually allow you to assign a semantic value. Yeah, so it has nothing to do with money. It's basically a template for saying assign the semantic value of this grammar construct to be, whatever value I assign it. And the value that I'm assigning it is an AST node. So every time a grammar construct is matched, we construct an AST node and then assign it to be the semantic value for that grammar construct. And now what do we do with these grammar constructs? So in order to actually make use of these AST nodes, we can use money sign and a number like money sign 1 to reference each semantic value of each grammar construct in the production rule. So let me illustrate that with an example. This says, construct a new AST node for the prog AST node, and its child nodes are these 3 semantic values. So to make this a little more explicit, I can say, so I can capture whatever declaration lists. So this declaration list also had a semantic action, and its semantic action is supposed to set a new AST node that represents the declaration list construct. And in the parent of that, I capture that AST node, or I capture that semantic value using money sign 1. Similarly, I capture the semantic value of function list using money sign 2. And I capture the semantic value of main function using money sign 3. So somebody's asking, can I do AST node equals create prog? So yeah, okay, so let me decompose this a little bit. Let me decompose this. So I'm kind of doing many things at once here. Yeah. So first I'm just saving the semantic values of each of the children constructs that I want to save. And I'm expecting that their semantic actions have already set the node. Then I'm taking each of those semantic values that I captured from the child nodes. Let me fill this out to make this just legal C. And so, these are just variable names, so the naming doesn't matter. And then so let's just look at this code. So I assume that just like in recursion, I assume that the child function I call is already written and correct. So I assume that the semantic actions of the child constructs have already set their semantic values. I capture them in the parent, and then I create a new node out of those, setting each of those child constructs as child nodes in my grammar. And then it's basically like returning the semantic value, returning the AST node. I set it to the double money sign. So you can think of these as like the recursive function calls in our toy compiler. This is the same as our toy compiler, where we can create a new node. And this is like the return in our toy compiler's parser. So recursive function calls get the return values and then return a new return value. And the kind of, very glib way of saying this is just to do this all at once in a single thing. Okay, so somebody asked where create prog is defined. So let me show one more example with main function here. So one thing to keep in mind is that these numbers are numbering each of the symbols in the construct. So main is the first symbol, curly brace is the second symbol, declaration list is the third symbol. So this is the kind of abstract part of the abstract syntax tree. This is the abstract syntax tree versus the concrete syntax tree, which has all of the terminals from the input. We're abstracting away some of the terminals that we don't need for compilation by just throwing away or omitting those symbols. So that's why that's why declaration list is symbol 3 here. So that's a little gotcha when writing these. It can be very easy to think that, well, that's the only one that has a semantic value I care about, so I'm just gonna put 1 here. You wanna make sure that these numbers correspond to the numbers in your input. How do I highlight without mouse? In Emacs, you do control space and then move around and then control space, and then control control something else. Control space and then control G to end or alt W to copy. Okay, so somebody asked, is program AST? Yeah, okay, so yeah, another thing. This is described in the project. So I know you probably learned never to use global variables, but this is common in this kind of old school compiler writing stuff. In my main function, so the main function is given to you already, but there's just basically a global variable called program AST. This is what you set in prog. It's the only place you set it, and then this is where we print it out. So this code is all given to you, but yeah, this is where it is. So it's actually defined at the top here as a global variable defined by this compilation unit, and then it's and during linking, the main compilation unit has access to this so that it can call the print function. But since I only have 2 minutes, oh my god, okay, this. Yeah, so let me go over the AST API. So in AST.h, which I've also given to you, I define the AST data structures. So these are what you'd expect. So a prog just has 3 children: declist, funcalist, main. And at the bottom here are all of the create functions. So they're pretty rote. They're just the name of the AST node, and as parameters, they take the child nodes. If you're really curious, they're inside of AST.c. They're actually implemented. So this is where you're, allocating memory and setting the children. Really boring stuff. I actually automatically generated this stuff. I used a Python program to automatically generate this. If you're really interested, come to All Stars. I can give you the code for that. But I just generated this stuff. One of the main things to keep in mind, especially when you're using this AST, is when we have constructs that have alternates like expression. Okay, so because this is being recorded, I'm gonna go over a little bit. So, but if you need to go, please feel free to go. What I'm covering now is loosely covered in the project description, but I'll just go over it for people to have, for those who have more questions about this. So if we look at expression, the whole expression tree has there's a lot of different kinds of expressions in our syntax. So to make this simpler in our AST, there's only one node for expression, and a union type is used to capture all the different varieties or all different kinds of expressions that we have. You won't have to actually worry about this very much when you're generating the AST. The creation functions handle this for you. So just look at try to look at the name of the function and its type to figure out which AST construct is appropriate for that grammar construct. So I didn't make this super explicit. This is something that you kind of have to figure out. But if there's too many questions about this, so you have like 3 or 4 weeks to do this, 3 weeks, I think, to do this till October 16th to get this program done. So try to make a little guess. So character expression is, for character constant. Binary expression is for the binary, where is it? Is for expression here. So I'll, if this is a little, so the lab will cover this a little more. Labs will be able to cover this a little more and ask questions about it. If it becomes too mysterious, I'll make more of a specification of it. So in the project description. But I'm kind of hoping you'll be able to figure this out. But if not, ask in labs, ask in office hours. If many people are asking, I'll just put in the specification. But yeah, that's the assignment. So basically each one of these to-dos is going to consist of some AST creation function. And they're all going to look fairly similar. And your job is basically to pick the right AST node to use to construct the AST node for this, corresponding to this grammar construct. So I've left it a little mysterious which AST nodes correspond to which grammar constructs. But we can unravel this a little more in labs. And if it's way too mysterious, then we'll do it in lecture. And I actually wanted to show coding of some of these. So let me show a couple of these so it's at least recorded for the lecture for those who go back and view it. But yeah, ask in lecture a little bit more about these ASTs in detail and coding them up. Let me see if there's anything else. So yeah, there's a bunch of troubleshooting in the project description that are sort of tips for troubleshooting. The project description is, it's linked from the assignment. It's here. Tells you how to get started, gives you the full API for the abstract syntax tree. But let me show you a couple of, for those of you who have to leave, of course, leave. I'll leave this recording for those who want to go back and view this. But let me implement a couple of the semantic actions for you so you can see what this looks like. So I've given you program already. So this is what program looks like. Given main, I think. Here's main. Let me do declaration. So the lists are a little tricky. Yeah, I'm going to have to send a note to tell people to watch this. Oh yeah, so office hours, I had to move office hours. I'm going to send out an announcement there from 3:30 to 4:30. I'll send out an announcement for this. So sorry for not, I dropped the ball on this. I have a meeting I need to go to at 1, which is just this week. But they're from 3:30 to 4:30. I'll send an announcement. But I did send an announcement that they are not at 1 to 2. But I'll send an announcement right after this with that information. Okay, so lists are a little bit tricky to do with our, oh, don't tell me it froze. Well, hopefully this will still be recorded. So to do lists, the semantic value for the list is just null for the empty one. And there are creation functions for lists. So they look just like any other AST nodes, except in this case, the empty grammar production will correspond to a semantic value of null. And this will just kind of be captured when it's basically creating a linked list through semantic actions in a grammar. Okay, that's declaration list. Let me do declaration here. So declaration is and you can see some of the names are kind of abbreviated. So sorry for making that a little bit, maybe a little bit obfuscated. But if you just look at the specification there, there's like 20 function names. It's basically just matching which function name to use. So that's creating the one for declaration. So again, this is setting the semantic value of the declaration construct to be a new AST node, which is the decal of decal type, and it has 2 children that correspond to whatever the semantic value of type is and whatever the semantic value of identifier is. You can't change, you can, so I've given you the source code for the AST functions. So if you change the name, you're gonna have to change them in the source code. And I don't recommend changing them. I would recommend leaving the same template code that we have. It'll also ensure that we grade more correctly, so that we can use our own code, the template code provided to you. If you really don't like it, you can use a macro to change the name. Ask me in office hours, and I can show you how to do that. Let me do type. So let me do an integer type. So I want to do enough so I can show the show a complete AST for this. Where is this? It's freezing. Let me just implement these all real quick. So if you're having freezing problems, I think the recording should be fine. So there's the implementation of function. It works just like declaration lists. I'll give you statement lists. And so I know I'm going through this really quickly. So next time I can reiterate this and make it clear to everyone where to find these implementations. Here's statement list. It looks just like all the other lists. Yeah, I may just have to give this code, just so people can see it for themselves at their own pace. We need primary expression, postfix expression. So I'm just filling out a bunch of these semantic actions. And I'll explain this in more detail next time, but I just want to give you the code and have it recorded for those who rewatch this. And yeah, and in lab, Josh will cover, hopefully he's prepared to cover this because we didn't talk about this yet, but he should be able to cover this. He should be able to cover this stuff in more detail. So int constant. All right, everybody. So yeah, if you need to leave, please, by all means, leave. I know I'm staying over, but I just want to have this recorded. And then in lab, Josh will cover this stuff in more detail. Okay, so that should be all I need to implement. I just want to run it and make sure it works. Nope, I broke something. I forgot. Okay, yeah. So yeah, good. Talk to you guys later. Sorry for going over so much. Go to lab and I'll have this stuff in more detail. I'll send out an announcement about office hours. So everybody have a good weekend. Apologies for going over a little bit. Let me answer. So yeah, for those of you, yeah, so this is the end of the lecture. I'm going to answer some other questions here. Everyone have a good one and take care.